Now let's study the mechanism of how these glycosidase enzymes carry out their chemistry. These are the enzymes we use to determine alpha or beta for our disaccharide lactose. And the glycosidase that we're going to study is lysozyme, which is a naturally occurring antibiotic. It's found, for example, in human tears. It causes bacteria cell walls to weaken and the cell to lyse. What it does is it cleaves specifically at the sugar glycnac, which is the sugar shown here, which has a 2 amino group as the acetamide, so the acetamide position at C2 rather than having a hydroxyl group. That specific glycoside bond is cleaved. It's a beta glycosidase. It cleaves this beta glycoside bond. But the key point that I want you to take away from this slide is that it does so with retention of stereochemistry at that anomeric position. This beta glycoside bond is cleaved, and the hydroxyl group on the resulting product, muramic acid, is this beta hydroxyl group. So how does it cleave with retention of stereochemistry? Some of the details of the mechanisms are still under debate, but the key point and an idea on how this retention of stereochemistry comes about is shown here. In the active site are 2 carboxylic acid side chains. At position 35 is the neutral form of the side chain glutamate, glutamic acid, and at position 52 is another carboxylic acid from aspartate. It's in its negatively charged form, and it can serve as a nucleophile. Well, the way this reaction is believed to take place to hydrolyze this bond here is to use that glutamic acid as a general acid that can protonate that leaving hydroxyl group. So protonation of this oxygen atom produces the hydroxyl group at that C4 position, the C4 position of muramic acid. Now, the oxocarbenium ion intermediate, that's a word that you should be familiar with and you might want to write down. This oxocarbenium ion intermediate is a very potent electrophile, and the nearby nucleophile, which is on the alpha face, the underside, will undergo attack and stabilize as a covalent adduct through that aspartate oxygen. In an alpha linkage, the oxocarbenium ion is trapped in that way. What happens next at the position is formation of oxocarbenium ion again. So we go back to the same intermediate, but it's held in this form. In fact, this has been isolated. This covalent adduct has been isolated, but it will revert back to the oxocarbenium ion, and then in the presence of water we have the general base, the glutamic acid now as its glutamate at position 35, deprotonates the water, which adds in to the alpha face. And so this whole point of the aspartate 52 is really to block the alpha face. It's the beta face that's left open, that when water enters into the active site, that's the only site, that's the only face that's available for reaction. And so the hydroxyl group enters. We have a beta anomeric configuration that's preserved. Basically what you can see is we've done a double inversion. That is, here you can see the stereochemistry was inverted, but then in the final product, since that alpha face was blocked by this nucleophilic aspartate group entering only the beta face, we've basically done a double inversion. Net result is retention of configuration.